In Chapter 1, we said our goal as static program analysis scientists was to be able to take in a program and determine if the program was in some sense correct. We'll make progress towards that goal in this chapter. In particular, we'll try to figure out whether a program can have a type error that occurs during runtime. If you remember, due to Rice's theorem, we'll never be able to actually determine if any non-trivial property of a program is true, and this includes having runtime type errors. The best we can hope for instead are conservative approximations. We'll introduce the notion of typability. If we have a typable program, we'll know that no runtime type errors can happen. On the other hand, just because a program is not typable doesn't necessarily mean runtime errors will happen. This conservativeness will be true for our type checker in our toy language tip, just as it's true for any programming language, including Java. So here we can see an example of a Java program that won't actually have any problems type-wise during runtime, but the Java type checker will still reject it. So how do we determine if a program is typable? Our approach will be in two parts. First, given the AST of the program, we'll try to generate constraints on the types of particular pieces of syntax. Second, we'll use these constraints to determine the types of every expression in the program, and if we can find a solution to this constraint problem, we'll know that every expression in the program does have a type. So to start out with, here's our language of types. The value of a type will either be an integer, a pointer to a type, or a function from type, and returns this type. We'll associate something called a term constructor with each of these values, and each term constructor will have an arity. The arity of a term constructor is just the number of taus that exists in the associated type. For example, the term constructor for this pointer type is pointer, and since there's one tau in this constructor, the arity of this term constructor will be just 1. For this example, it would be the number of types we're passing into the function plus 1 for this return type. So if we had the program 1 and we wanted to know the type, which we'll denote with these double square brackets, it's just going to be int. Say we had this function foo. The type of foo will just be something that takes in an integer and returns an integer. So that's this type. But what's the type of the factorial function, for example? Clearly it's a function, so it starts by looking something like this. And there's 2 arguments. The second argument is an integer, and it clearly returns an integer. But what goes here? Well, we pass into the function itself, so all of this needs to go into this empty spot right here. So if we plug it in, we'll get this. This still has the underscore in it, so we're not actually making progress in determining what the type of this function is. In fact, this type isn't even expressible in our language as we've defined it so far. So let's extend our types to include a new type value. We'll introduce mu alpha of tau and type variables called alpha. I'll explain what all of these mean in just a second. This value mu alpha tau just represents the type tau, but every time we see an alpha in tau, we'll replace it with mu alpha tau. And that seems similar to the problem we were dealing with earlier in the factorial function, where we needed to keep on replacing something into itself. And so if there exists a term alpha in tau, and we keep on replacing this term into itself, it seems like we could build up the kind of value you want. In fact, that's exactly true. So the type of our factorial function can be represented as follows. So this is a function that takes in 2 arguments and returns an integer, and the type of the first argument is this whole thing. So again, we keep on plugging that into alpha 1. These alphas help us with a different problem. So consider the store function right here. The types of A and B do have some constraints on what they can be, but it's not necessarily the case that A is always an integer or always a function or anything like that. It's just that these 2 variables will have some relationship between their types. In particular, it looks like the type of B is a pointer to whatever the type of A is. So we could represent that like this. So the way we're going to determine typability is going to be to look at every piece of syntax in a program and create constraints from these syntax on the types of the expressions in that syntax. We'll have a systematic way of doing this using the rules as follows. You can pause the video here to see what exactly these rules will be, but I think they make sense intuitively, so I'm not going to go through all of them, just the first three. So for example, if we see an integer literal, we'll know that the type of that is just going to be int. If we see two expressions and a binary operator between them, for example, plus, minus, divides, or times, we'll know that the types of the left and the right side of those operators are going to be the same. And we're also going to know that the type of the expression as a whole is just going to be integer. If we see the input token anywhere in our program, we'll know that the type of that will be integer. So if we look at this program, we'll generate the following constraints. Short is a function that takes in nothing and returns whatever the type of z is. The type of input is always an integer. The type of x is whatever the type of input is, and that's coming from the second line of the program. The type of alloc of x is going to be a pointer to whatever the type of x is, and so on and so forth. And basically we're just using all of those rules to systematically determine these constraints. So let's keep in mind what our goal is. We're trying to determine if a program is typable, and our first step along that journey was to create these constraints from our input program. Now we're going to take those constraints and try to assign a type for every variable we encounter. It turns out solving this constraint satisfaction problem is possible in almost linear time due to the union-find data structure. Our union-find data structure is going to keep a partition of our type variables into groups. For the sake of concreteness, let's say we have the following sample program fragment. X equals y equals 15. Using those rules I showed earlier, we'll get the following constraints. The type of x is equal to the type of y, and the type of y is equal to the type of 15. The type of 15 is equal to int, because it's an integer literal. Again, our union-find data structure is going to maintain a partition of all the type variables we've seen in our constraints into groups. So I've sort of divided up our constraints into all the different constituent terms, and we're going to call makeset on each of these terms. So the makeset operation introduces like a canonical representative of that group, which I'll sort of signify with a dot. So each of these are in their own set right now. Then for every constraint, we'll unify the two terms in that constraint. For example, we'll unify this and this and this and this and this and this. So what does it mean to unify a term tau1 with tau2? We're basically going to start by finding the leader of tau1 in the union-find data structure and the leader of tau2 in the union-find data structure. So for this constraint, we'll start by finding the leader of x, which is this dot, and the leader of y, which is this dot. If the leaders of tau1 and tau2 are the same, we'd be done. But in this case, they're not the same, so we'll need to unify them. Unifying two terms basically means unioning two leaders together. Except we'll also maintain the invariant that whenever we unify a term that's a proper type, like int, with something that's just a type variable, like y, we'll prefer to make the leader of the union the proper type, so int, for example. But in this case, we just have two type variables, so we can make an arbitrary one of them leaders. Of x and y, let's just make y the leader. And now we see y and 15 need to be unified, so we'll take y and 15. And so now x, y, and 15 are all part of the same group in our partition. And lastly, for this constraint, we have 15 and int. And so now because int is a proper type, we should make the leader of 15 and the leader of int whatever the leader of int was. So we'll do this. If you now look for the leader of x or the leader of y, and you follow down the arrows, you get whatever the leader of int was. And so you know from that that the type of x and the type of y are both int. There are two additional pieces of nuances with the unify algorithm. So say we needed to unify the following two terms, x1 of x2, x3, and y1 of y2, y3. So these are two types. When we unify these, not only will we union together the leaders of x1 and y1, but we'll need to recursively call unify on x2 and y2 and x3 and y3. x2, x3, y2, and y3 are called subterms, by the way. Additionally, if we ever unify together two terms of the wrong arity or of the wrong type constructor, we'll have a unification error, and we'll know that this program is not typable. For example, if you try to call unify on a function that takes one variable with a function that takes two variables, we'll have a unification error. In the end, we'll either be able to determine the types of each of our variables by finding their leader, or if we had a unification error along the way, we'll know that our program's not typable. For reference, this is the unify algorithm as a whole. Let's try this out with the following example. So say this is our input program. The first step in our typability procedure is going to be to create constraints from this. Again, this is a pretty mechanistic procedure, and it's determined by these rules. So for the assignment rule, we'll just set the type of x to whatever the type of input is. We'll recurse on the type of input. From the input rule, we'll know that this type is int. The type of y will just be a pointer to whatever the type of x is. And here, that's again the assignment rule. So the type of z is just whatever the type of star y is. So these are our constraints, and our first step in the unification process will be to call makeSet on each of these values. So I'll just sort of draw out our partition like this. So we'll now unify starting from 1. So x and input are going to be union together. So I can just draw that arrow there. Input and int are going to be union together. So since input's leader is x, I'll make x's leader int. Y and a pointer to the type of x are going to be union together. And I realized I don't have a representative for a pointer of x, so I'll draw that in. From 4, we'll have the leader of z will be the same as the leader of star y. So I'll draw in that arrow here. And from here, we'll have the leader of star y will be a pointer to dereferenced of star y. And I realize I don't have pointer to star y, so I'll draw in that term now. And now at the end of all of this, we can just read off the types of every variable by following the leaders. So for x, for example, we can see it points to int. Y doesn't end at a proper type, it ends at pointer to x. And when that happens, you just take whatever variable that is in here and follow its pointers. And so we have int, so we know that y must be a pointer to an int. Z must be a dereferenced of y, so y was a pointer to an int, so Z must be a dereferenced pointer of an int. Our type analysis so far is conservative, so it will still reject some programs that otherwise won't throw any runtime type errors. For example, take a look at this program. The problem here is that essentially our type system will try to unify a pointer to an int with an integer and then fail. A flow-sensitive analysis would have noticed that we don't actually use x as a pointer to an integer, we just use it as an integer. One other thing to think about is we don't have polymorphic types. Consider this program that otherwise seems like it should work. Our type checker will reject this. If we start our analysis at main and then recurse downwards, we'll generate constraints for x. Instead, we should start by analyzing f, determining its type, and then instantiating each argument of f whenever we see it called. This is called let polymorphism.